You have a substitute?
Yeah, substitute teacher. Don't misbehave. So I apologize for not being deaf and not being well organized this way, but I'm good. Yeah, it's good to give sort of more theoretical perspective on some of the things you can say. So. In particular, talk about this thing called Morse 2 functions, and so I thought I would start by trying to draw some pictures that someone was teaching about before. They're hard to draw and fun to try to think about. But this is to try to understand this trisection of the two torus. So I think we want that, this, and then the full rainbow. Right. Claims that this is should be equal to T2, and I want to see if we can like really see why that's true. And so what I really want to do is show you a particular embedding. So first of all, this is a T2. So this pair of tangles, trivial tangles, the claim is describes an embedded surface in R4, which is homomorphic to diffeomorphic to T2. But in fact, it actually describes a T2 which sits inside R3, inside R4. I'll say a surface S. And then that surface happens to be diffeomorphic to T2. That's the best way to say it. T2 being some standard object and S being this object constructed inside. And the reason you can think of it as being an R3 is that you can think of, because this is planar, you can actually think of the three planes fitting together. They're two-dimensional planes, they really fit together in R3, and you can actually fill them in with disks in R3 and actually construct this embedded surface. It's made out of 3 disks. Let's actually just remember quickly a couple of things about this. We put the pairs together. This one here. That has one pair, the next pair. That, and then the last pair is this. So they're all single components, and you can just see very explicitly the disks that they bound. 3 different snake configurations. But you can also abstract these as polygons, and that's the other useful perspective. This is 1, 2, 3, 4, 5, 6. That's a hexagon. And 3, 4, 5, 6. That's a hexagon, and gosh, there's a hexagon as well. So there are 3 hexagons that fit together. So what before I do the abstract theoretic perspective hexagons that fit together in the torus, and you might ask, well, whether I just look at this usual picture of the torus, can I see those 3 hexagons? And the answer is yes, and you can see those 3 hexagons. So this is, I'm ignoring the embedding R4 issue at all here, and just thinking about it. So if you, I don't have so the hexagon. Blue. this is number 1, and then hexagon number 2 should be blue and green. So that's this blue, and that blue. I wasn't adding new information when I put blue there because I already covered this blue. And the identification with opposite sides to make this a torus is like creative translation. That blue, and I guess so this is hexagon number 2, and then hexagon number 3 looks like it has 4 pieces, but when you cut them off and reassemble them, you realize it's a single hexagon. This one is here. So that's a way the bridge trisection of the torus coming from this particular triplane diagram. Okay, so and it's fun to try and just think. I mean, it's an interesting thing. You might call this sections of surfaces, and I want to show you another way that you might get that same abstract trisection of torus, which highlights a more smooth topology perspective. I'll write it down, but I mean, an abstract trisection of the surface would be decomposition of the surface into 3, each of which is a disjoint discs, which meet in pairs along disjoint unions of arcs, and triple intersection is, maybe I'll write it down. Because it also, we're supposed to be segueing into 4-dimensional context, thinking about 4-dimensional projects, so abstract section surface S is decomposition S1, union S2, 3. I hope this lines up with Jeff's notation, but if not, fix it. And first thing is for each I, as I is diffeomorphic to a disjoint union of some number Ci copies of a disk, D2. And then second thing is that for each I think Si intersects diffeomorphic to some number of copies, B of them, that's the number of bridges of, let me call it B2. So P1 being the interval, B2 being the disk. And then, of course, a consequence of this is that S1 intersect S2, intersect S3 is equal to 2 points. So this is our S1. And then, you could have started the definition of bridge trisection by describing abstract trisection first, and then saying if you're embedded in R3 in such a way, R4 in such a way that, yeah, maybe I can say that too, actually. So alter the definition that you can say S4 or R4. Let's say S4. So alter the definition. Section. So S is 4. So the first thing to know is that, so step 1, step 0 is consider S4. And if there are 2, 3, there's coordinates 0 to 2, 5, 3, and so forth. And then if you let then S4, you can write it as say X1, union X2, union X3, where Xi is equal to S4 intersected with R2I, 3 pieces. I claim that